In the vast expanse of our solar system, amidst the swirling gas giants and icy moons, lies a celestial wonder named Io. In January 1610, Galileo Galilei pointed his telescope towards Jupiter. He observed 4 tiny points of light dancing around Jupiter, changing their positions night after night. These were moons, not stars, orbiting the gas giant. This discovery revolutionized our understanding of the solar system. Among them, Io captured the imagination of scientists. Io is a world of fire and fury, a testament to the power shaping our universe. Io is the innermost of Jupiter's 4 largest moons, known as the Galilean moons in honor of their discoverer. Imagine Jupiter as a celestial king, ruling over its court of moons. Io is the closest to this king, caught in a gravitational dance that dictates its fate. This proximity to Jupiter, along with the gravitational influence of its neighboring moons, Europa and Ganymede, creates intense tidal forces on Io. These tidal forces are not like the gentle rise and fall of ocean tides on Earth. Instead, they are powerful enough to stretch and squeeze Io's interior, generating immense heat through friction. This heat is what fuels Io's most spectacular and defining feature: its volcanism. Unlike the cold, dormant landscapes of many other moons, Io is a world ablaze. Its surface is a vibrant tapestry of yellows, oranges, reds, and browns, colors derived from the sulfur and sulfur compounds spewed out by its hundreds of active volcanoes. Imagine a landscape more alien than anything found on Earth, where towering plumes of molten rock and gas erupt into the sky, reaching heights that dwarf even the tallest mountains on our planet. This is Io, a world in constant geological turmoil, where change is the only constant. Io holds a unique distinction in our solar system. It is the most volcanically active body we know of. While Earth boasts active volcanoes and even our neighboring planet Mars shows evidence of past volcanism, Io's activity dwarfs them all. Imagine a world where volcanic eruptions are not isolated events, but a constant feature of the landscape. Io's volcanoes erupt with such force that their plumes can sometimes be seen through Earth-based telescopes. Some of these plumes reach hundreds of kilometers in height, painting streaks of sulfur and gas across the moon's surface. One of Io's most impressive volcanoes is Iocaste, a vast, lava-filled depression that regularly erupts in spectacular fashion. Iocaste is so large that its eruptions can actually cause a measurable change in the infrared light reflected from Io. This intense volcanic activity is a testament to the immense power of tidal heating. Io's story provides us with a unique glimpse into the powerful forces that shape celestial bodies. It expands our understanding of planetary geology beyond the familiar examples found in our own backyard. Io's appearance is unlike any other celestial body in our solar system. From space, it appears as a vibrant, multicolored orb. Sulfur compounds from volcanoes create a palette of colors. Imagine a landscape painted in hues of yellow, orange, red, and black. These colors shift over time with new eruptions. The most prominent color is yellow from sulfur dioxide frost. This frost covers vast plains, resembling a cosmic pizza. Patches of red, orange, and black are from other sulfur compounds. These colors paint a world in constant flux. The vibrant hues provide scientists with valuable information. Studying these compounds reveals Io's volcanic history. Section 2. The Scars of Tidal Torment. Io is the most volcanically active body in our solar system, and its surface bears the scars of this intense geological activity. Unlike the cratered landscapes of our moon or Mars, Io's surface is remarkably smooth. This is because volcanic flows constantly resurface the moon, erasing any impact craters that may have formed. Instead of craters, Io is covered in volcanoes, lava flows, and volcanic plains. These features create a rugged and alien landscape unlike anything found on Earth. Imagine vast plains of solidified lava stretching for hundreds of kilometers, their surfaces crisscrossed by channels and fissures where molten rock once flowed. Towering above these plains are volcanic mountains, some of which dwarf the largest mountains on Earth. These mountains are not formed by tectonic plates colliding as they are on Earth, but by the buildup of volcanic material over millions of years. Io's volcanoes are constantly erupting, spewing molten rock, gas and ash into the thin atmosphere and beyond. These eruptions create plumes that can reach hundreds of kilometers in height, leaving behind dark fan-shaped deposits on the surface. The constant resurfacing by volcanic activity means that Io's surface is incredibly young, geologically speaking. Scientists estimate that the surface is only a few million years old, which is a blink of an eye in geological time. Section 3. A world in perpetual motion. Io's orbit around Jupiter is not a peaceful waltz, it's more of a chaotic mosh pit. This is because Io is caught in a gravitational tug-of-war between Jupiter and its neighboring moons, Europa and Ganymede. This gravitational dance forces Io into an elliptical orbit, meaning its distance from Jupiter changes as it orbits. As Io moves closer to Jupiter, the gravitational pull increases, stretching the moon like a rubber band. As Io moves further away, the gravitational pull decreases, allowing the moon to relax back into its spherical shape. This constant stretching and squeezing generate immense heat within Io's interior through a process called tidal heating. Imagine billions of tons of rock being pulled and pushed, generating friction that heats up the moon's interior to thousands of degrees. This heat is what fuels Io's intense volcanic activity. The tidal heating is so powerful that it melts rock deep within Io, creating vast magma chambers that feed the moon's many volcanoes. This internal heat also makes Io's surface incredibly dynamic. The surface is constantly shifting and changing as molten rock rises from the interior and erupts onto the surface. This makes Io a fascinating world to study, as it provides scientists with a unique opportunity to observe geological processes that are happening in real time. Section 4. The Mystery of Io's Mountains. While Io is known for its volcanoes, it also boasts another surprising feature: mountains. These mountains, however, are not formed in the same way as those on Earth. On Earth, mountains are primarily formed through plate tectonics, where the Earth's crust is broken into plates that collide, buckle, and uplift to form mountains. Io, however, lacks plate tectonics. So how did its mountains form? Scientists believe that Io's mountains are formed by the constant volcanic activity and the intense tidal forces acting on the moon. As magma rises from Io's interior, it pushes up on the surface, creating domes and plateaus. Over time, these domes and plateaus can be uplifted and tilted by the tidal forces, forming mountains. The constant resurfacing by volcanic flows also plays a role in shaping these mountains, eroding their slopes and creating valleys and canyons. Some of Io's mountains reach heights of over 10 kilometers, making them taller than Mount Everest. The formation and evolution of mountains on Io is still an active area of research. Scientists are using data from spacecraft missions, along with computer models, to better understand the processes that shape these unique geological features. The study of Io's mountains provides valuable insights into the internal structure and evolution of this fascinating moon. Io's volcanoes are a sight to behold, even from afar. Unlike the explosive eruptions we often see on Earth, many of Io's volcanoes erupt in a more continuous and spectacular fashion, creating what scientists call fire fountains. Imagine a giant fire hose spewing molten rock hundreds of kilometers into the sky. These fire fountains occur when sulfur and sulfur dioxide gas, trapped beneath the surface, suddenly find a way to escape. The pressure builds until it overcomes the weight of the overlying rock, and the gas explodes outward, carrying molten rock with it. The molten rock is stretched and torn apart by the escaping gas, forming long, thin strands that resemble fiery curtains. These curtains can reach heights of tens of kilometers before they fall back to the surface, creating a mesmerizing display of fire and fury. The colors of the fire fountains vary depending on the temperature and composition of the erupted material. Some fountains appear bright yellow or orange, while others glow a deep red or even blue. The fire fountains of Io are a testament to the moon's intense volcanic activity and the unique processes that govern its geology. They provide scientists with valuable insights into the composition of Io's interior and the behavior of volcanoes in low-gravity environments. Among Io's many volcanoes, one stands out as a true giant, Iocaste. This colossal volcanic depression, named after the Norse god of mischief, is the largest volcanic feature on Io and one of the most active volcanoes in the solar system. Imagine a lake of molten lava so vast that it could swallow entire countries on Earth. Iocaste is a sight to behold, even from space. Its horseshoe-shaped caldera, a massive depression formed by the collapse of the volcano's summit, stretches over 200 kilometers in diameter. Within this caldera lies a sea of molten lava, constantly churning and bubbling as heat rises from Io's interior. Iocaste is known for its periodic eruptions, which occur roughly every 540 days. These eruptions are so powerful that they can be detected from Earth, causing a noticeable increase in Io's brightness. During these eruptions, the lava lake within the caldera overturns, releasing a massive amount of heat and volcanic material into the surroundings. The overturning process is thought to be caused by the gradual heating and cooling of the lava lake. As fresh, hot lava rises from below, it heats up the cooler lava on the surface, causing it to become less dense and rise. This eventually leads to the entire lake overturning, much like a pot of boiling water. Io's volcanoes exhibit remarkable diversity in size, shape, and eruptive style. Scientists have identified several types of volcanoes on Io. Common types include paterae, fluctus, mountains, and plumes. Paterae are large, irregular volcanic depressions. Iocaste is a prime example. They form by ground collapse after eruptions. Fluctus are vast plains of solidified lava, formed by highly fluid lava spreading over large distances. The surface can be smooth or wrinkled. Mountains are formed by uplift and tilting. They can reach heights of over 10 kilometers. Plumes are visually striking features. They can reach hundreds of kilometers in height. Plume shape and height depend on eruption conditions. Section 4. A Symphony of Fire and Gravity. Io's volcanism is not a random or isolated phenomenon. It is the result of a complex interplay between the Moon's internal structure, its orbit around Jupiter, and the gravitational influence of its neighboring moons. This intricate dance of celestial bodies creates a symphony of fire and gravity that shapes Io's destiny. At the heart of this symphony lies tidal heating, the process by which the gravitational pull of Jupiter and its moons generates heat within Io's interior. This heat, combined with the Moon's internal heat from radioactive decay, melts rock deep beneath the surface, creating vast magma chambers that feed Io's many volcanoes. The elliptical shape of Io's orbit, caused by the gravitational tug-of-war with Europa and Ganymede, amplifies the tidal heating effect. As Io moves closer to Jupiter, the gravitational pull increases, stretching and squeezing the Moon like a rubber ball. This stretching and squeezing generate friction within Io's interior, releasing even more heat. The result of this cosmic ballet is a world in constant geological turmoil, where volcanoes erupt with fury, lava flows reshape the landscape, and plumes of gas and ash paint the sky. Io's volcanism is a testament to the immense power of gravity and the dynamic nature of our solar system. Section 1. Voyagers' First Glimpse. Our understanding of Io remained limited until the space age. The twin Voyager spacecraft flew past Jupiter in 1979, revealing Io's volcanic nature. Voyager's images showed Io's vibrant surface and volcanic plumes reaching over 300 kilometers. This discovery revolutionized our understanding of planetary geology. Section 2. Galileo, a closer look. NASA's Galileo spacecraft, launched in 1989, studied Jupiter and its moons, including Io. Galileo's long-term observations revealed changes in Io's volcanic activity. Its instruments provided unprecedented detail of Io's geology and atmosphere. Galileo confirmed Io as the most volcanically active body in the solar system. The mission ended in 2003, but its data continues to provide new insights. While the Galileo mission ended in 2003, the exploration of Io continues. In 2016, NASA's Juno spacecraft began studying Jupiter and made valuable observations of Io. Juno's microwave radiometer mapped Io's volcanic hotspots, revealing magma chambers. Juno's mission is ongoing, providing new data on Io and Jupiter. The exploration of Io is far from over. NASA's IVO, or Io Volcano Observer, aims to study Io's volcanic activity and potential for life. IVO would track changes in volcanic activity over time. The European Space Agency's JUICE mission will also make flybys of Io. These missions promise to unlock more secrets about Io. Each mission deepens our understanding of the solar system. Io offers invaluable insights into planetary evolution. Tidal heating, driven by gravitational forces, shapes Io's volcanic activity. Studying Io helps scientists understand Earth's early volcanic history. Io's extreme environment tests models of planetary evolution. Tidal heating drives Io's volcanic activity. As Io orbits Jupiter, gravitational forces generate heat within the Moon. This process affects many moons in our solar system. Understanding tidal heating helps unravel the mysteries of distant worlds. It plays a crucial role in assessing their potential for life. Io's study has implications for the search for life beyond Earth. Io's volcanic emissions could deliver key ingredients for life to Europa. Europa's subsurface ocean is a prime target in the search for extraterrestrial life. Studying Io helps scientists understand material exchange between celestial bodies. This process could have implications for the origin of life elsewhere. Io is vital in understanding the Jovian system. Io's volcanic activity impacts Jupiter's magnetosphere. The Io plasma torus interacts with Jupiter's magnetic field, creating auroras. Io's gravitational influence affects the orbits of neighboring moons. Studying this system helps understand planetary interactions and the emergence of life. Io's story is a testament to human curiosity and exploration. From Galileo's telescope to modern spacecraft, Io has captivated scientists. Each mission reveals more about Io's complex nature. Io's story reminds us of the universe's surprises waiting to be uncovered. Io serves as a window into planetary forces and tidal heating. Its study has revolutionized our understanding of planetary evolution. Io's interactions with Jupiter influence the magnetosphere and other moons. Material from Io's volcanoes may affect Europa's chemical composition. Io continues to challenge and inspire future generations of scientists. The exploration of Io is far from over. Future missions will provide a closer look at Io's volcanic processes. Scientists aim to study Io's magma chambers and potential water ice. Io connects our understanding of the solar system's past, present, and future. The journey of discovery that began with Galileo continues into an exciting new chapter.